Okay, so in this one now we have to use the double angle formulas for the trigonometric functions, and we have to calculate the value in these exercises 47 through 50. So the first one is this. So let's see now, but before we start writing the solution, note that pi divided by 8 radians is not a standard angle. That means we already don't know its value from the table where we have the values of the trigonometric functions for the known angle. So this is not exactly a known angle. So here we have to use that double angle formula to somehow turn it into a known angle. Okay, now if we do not remember the double angle formulas, say that is the case, say I have forgotten what the double angle formulas are, that's not a problem. You just remember this thing: cos A plus B is cos A cos B minus sin A sin B. Now if we take A equal to B, then writing B for A, we would get, that is, if A is equal to B, then this implies cos, we would then get 2A, that will be equal to cos A, which is cos square A minus sin A sin A, that is sin square A. Now from this we can either turn the right hand side into an expression that involves only cosine or an expression that involves only sine. So let's see what we get from that. So if we say write 1 minus sine square A in place of cos square A, then we are getting what? 1 minus 2 sine square A. So cos 2A is 1 minus 2 sine square A. Now from this, if we rearrange things, we would then get ultimately sine square A in terms of cos 2A like this: 1 over 2 times 1 minus cos 2A. Okay, so this is an expression for sine A. You can say sine A because sine squared A, after all, it involves sine A in terms of cos 2A. So the angle has doubled. So that's why it's a double angle formula. You can, however, do that other thing here also. Say you do not change cos square A, but you change sine square A. Doing that, we would get this, and that equals, because minus minus would give you plus, so 2 cos square A minus 1, and from this we get cos square A equal to 1 half of 1 plus cos 2A. This is another formula involving a double angle 2A. So we are going to use that here. But in the solution, of course, we are not going to write these things. If you want to derive these things, say you have forgotten and you want to derive, so you can do it alongside the solution as a rough work. So we will just directly write we have this equal to 1 half of 1 plus cos 2 times, let's just write that so that there is no confusion afterwards. Okay, so now you can see that when you write pi divided by 4 in place of this, that is a known angle. Okay, so that equals 1/2 of 1 plus cos pi over 4. 1 plus 1 over square root of 2. You can just keep it like this itself, or if you want you can simplify this, although that is not really a simplification. That word is somewhat ambiguous in this case in particular. What I mean, if you just change this expression, would you really call that a simplification? Is anything getting cancelled? I don't see that. So what I suggest is that you just keep it like this, unless of course in the exercise itself something has been explicitly said that you have to turn the answer into this particular form. Nothing like that has been said, so we are just keeping it like this. So this is our value. Let us then see the next one. (48) cos square pi over 12. The exact similar thing. We have this equal to 1 plus cos 2 times pi over 12. Pi over 12 is also not a standard known angle for which we already know the cosine value. So we are taking the help of double angle formula. Pi over 6. Now cosine pi over 6 radians is equivalent to 30 degrees, and cosine 30 degrees square root of 3 divided by 2. So this one, like that. Next, (49). Now we have sine. The angles are these two angles only. So in this one we have sine squared pi over 12 radian. So here we have to use the other double angle formula. We have sine square pi over 12 equal to, I think I am losing ink already. I should have refilled. Anyway, just give me a moment. Okay, so this one will be equal to 1/2 of, this time we will have 1 minus. For the cosine square we have 1 plus, for sine square we have 1 minus. That equals 1/2 of 1 minus sine pi over 6. That one also I left just like that. If you want, you can somehow change it. Here, however, we do not have irrational square root of 2 or square root of 3, because sine pi over 6 is 1 over 2. So 1 minus 1 over 2 is again 1 over 2. That times 1 over 2 is 1 over 4. So here the value is rational. And then another one, like this one, 50. In this one, of course, again sine square, but that other angle. Here we have you can almost see that this will be equal to that, well, okay, no, not exactly equal, because here the formula is different, although the values will be the same. I mean, what I am trying to say here is that I was thinking, at once I thought that this value would be equal to cosine square pi over 8, but that exactly is not true. I thought of it immediately because what I was thinking of is the value only, because pi over 8 is going to be turned into pi over 4, and sine pi over 4 is just like cos pi over 4 equal to 1 over root 2, but the formula is different. 1 minus sine 2 times pi over 8. One minus sine pi over 4. So here we are getting 1 over 2 minus times 1 minus 1 over square root of 2. So this is the value. Okay, so let's now move on. Next we come to 50, and these next few exercises are under the heading theory and examples. The tangent sum formula, that is the name of this exercise. The standard formula for the tangent, so this you can understand, I mean in the text it's written in italicized font, I think. if I am remembering correctly. So this is what the exercise is about, and now the statement of the exercise starts. The standard formula for the tangent of the sum of two angles is this. Let me write it here. Tangent of A plus B is equal to tan A plus tan B divided by 1 minus tan A times tan B. Okay, we have to derive this. And in deriving it, you can pretty much guess what we are going to do. We are going to use the corresponding formulas for sin A plus B and cos A plus B. So since we are going to use those things, so let's just directly start from tan A plus B itself. Divided by cos A plus B. Okay, now sin A plus B we already know is sin A cos B plus cos A sin B, and cos A plus B is cos A cos B minus sin A sin B. You can to some extent afford to forget the other formulas, but these you cannot forget. These you will always need. Now what we do, now I won't have space if I write the next line here. Now what we do, we divide both the numerator and denominator by cos A cos B. Sin B divided by cos A cos B minus sin A sin B divided by cos A cos B. Okay, now there is an issue here. You see, the issue is that it does not matter how much you are playing with abstract symbols like this, because you can pretty much see, in fact this is a kind of a joke within mathematics, that sometimes you won't see any numbers at all. I mean symbols which are explicitly numbers. We know that these are going to be numbers after all, real numbers, but we don't see them here. Still, you should never forget that these are after all elements of the set of real numbers. That means these are real numbers, and this addition, division, subtraction, everything, whatever we are seeing here, that is happening inside the system of real numbers. So whenever you try to divide by something, you should always make sure that that thing is non-zero. That, however, we do not see here. So actually we cannot just simply write like this. We have to make sure that both cos A and cos B are non-zero. So a condition actually comes. Although nothing like that has been written here, but still we have to assume that condition, because without that condition whatever we are doing is in general not true. Provided cos A cos B is not equal to 0. It's enough to say that cos A cos B is not equal to 0, because that implies that both cos A and cos B are non-zero. If at least one of them is 0, then the product of course becomes 0. So we assume this. Then tan A plus B is equal to, okay, now if you perform the division, so to speak, on these individual terms, I mean you know what I'm saying here. So then cos B and cos B, they cancel out. We have sin A divided by cos A, so that gives me tan A plus, similarly here cos A and cos A will vanish, sin B divided by cos B is tan B. This becomes 1 because we have the same thing, minus sin A divided by cos A is tan A, and sin B divided by cos B is tan B. So we have in fact obtained what we were trying to derive, trying to show. But this condition remains, and note that this assumption actually has taken care of only this part of the formula where cos A and cos B are both non-zero. Now what happens if, say, at least one of them is 0? Now let cos A be equal to 0. Okay, so if cos A is 0, then what happens to A? we know precisely when cos A is 0, and in fact there is not a single value of A for which cos A is 0, and in fact there are infinitely many values of A for which cos A is 0, and these values are precisely the odd multiples of pi over 2, where n is an integer, n belongs to the set of integers. Now if this is the case, then what is happening to our formula? Is the formula still true? Let us see. So we can continue like this. In this case, what is tan A plus B? Let's see. Tan A plus B is of course tan 2n plus 1 pi over 2 plus B. And to make matters less complicated, let's just see, let's just use the relation for tan. Tan is sine divided by cos. Let's just do that. Okay, now if you use your same thing, usual formula, the expansion for sine something plus something, you then get sine 2n plus 1 pi over 2 cos B. Do I have space for this? Okay, we will manage. Cos 2n plus 1 times pi over 2 times, let me just write here, sine B divided by cos 2n plus 1 pi over 2 cos B minus sine 2n plus 1 pi over 2 times sine B. Okay, now in this case you can immediately see that in the numerator the second term vanishes because cos A is 0. This term in the denominator vanishes because again this is 0. So we only have these two things. In fact, to save space, we could have just written A itself here, no? But anyway, whatever we have done, we have done. Cos B divided by minus sine 2n plus 1 sine B. Now it seems like these two will cancel out. Yes, and they will. Provided, again, this sine 2n plus 1 pi over 2 is not equal to 0. Can it ever become 0? Since we now have a concrete angle, we can, whenever you have a concrete angle, you go back to the actual definition of sine and cosine. That means, okay, let me show it here because I have to continue the calculation now. So this is our unit circle, and we of course have our x-axis, our y-axis. So if our angle is an odd multiple of pi over 2, keep in mind that this n itself can be a negative integer, so that ultimately this 2n plus 1, this odd integer, can itself be negative. Fine. So we are just going to look at 3 or 4 cases for this integer. Say this integer is 1 when n is 0. Okay, that means our angle is pi over 2. So this is always the initial line for our angle, and the terminal line is this. So it intersects at the point 0, 1. It intersects the unit circle at that point. But if our odd integer, this entire thing 2n plus 1, it now so this is the case when n this entire odd integer is 1. It can be 3 also. So in that case, pi over 2, another pi over 2, another pi over 2. So then this will be the terminal ray, and that is intersecting the unit circle at this point 0, -1. Right? If we have 5, then 1, 2, 3, 4, 5. If we have 7, it will go 2 more pi over 2. That is 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. So it will come here. And like that, you will see that no matter what your odd integer 2n plus 1 is, it will revolve like this, and the final position of the terminal ray is either this or this, so that your sine of that corresponding angle is either 1 or -1. But what happens if your 2n plus 1 is itself negative, so that the angle you are, the rotation involved is clockwise rotation? Then also, if it is -1, so that your angle is minus pi over 2, then this is your rotation. So here again the final ray looks like this. If it is -3, -1, -2, -3, so it rests here. -5, -1, 2, 3, 4, 5. So it does not matter what this odd integer is. The terminal ray is either like this or like this. So, and correspondingly the sine value, because the first coordinate is cos theta by the definition of cos theta, and the second coordinate is sine theta. So sine theta is either 1 or -1, no question of having 0. So, and in fact, if we had this equal to 0, then actually there is a problem in the beginning itself. We don't have that, and that is why we can cancel them. Okay, and finally you see what we are getting, minus cos b divided by sin b. That means minus cot b. So this is the left hand side when a is 2n plus 1 times pi by 2. Now what about the right hand side? It should be equal to this, otherwise there is something wrong in the formula. So let's see that. And let's write like this, and the right hand side is this, tan a plus tan b divided by 1 minus tan a tan b. Okay. Oh, but here we will actually have a problem, no? Because if a is that, if cos a is 0, then tan a is not defined. So you see that in this case, in this particular case, if cos a is 0, then the right hand side becomes meaningless. It's not well defined, it's ill defined, because these symbols are undefined, rather I should say. They do not have any meaning in this case, and that is why, although in the text nothing has been said, we have to in fact include this condition, that cos a cos b is not equal to 0. And I think the authors did not bother to include it because it's understood that since we are being asked to derive the formula, so the right hand side should make sense, and for that we need this condition. So although it has not been assumed, but it's there in the background, so you can regard it like that. So it's not a mistake, the exercise is not wrong. The only thing is that in the beginning itself, whatever we have assumed, actually that's all, that's what we have. Because if we don't have this, then the formula itself does not make sense. I should have checked this side first, because I did not have to go through all this then. But anyway, so whatever we did before considering this case, there itself the solution ends, and we have in fact derived our formula. Okay, fine. So let us now move on. What is the next thing? The next thing is a continuation of this previous exercise. So that means, do you get it, what you have to do here? You don't have to go through all these things. You have to write in the beginning of the exercise itself, not after calculating all those things. You, in the very beginning, before you start writing other things, there itself you should write that since, you can write like this: since tan A and tan B are involved in this formula, we should have cos A cos B not equal to 0, and then you start your calculation. So then you won't have that problem of deciding whether you can divide by cos A cos B or not. Yes, you can, because now it's a non-zero real number, and that's it, that there things will end. But anyway, our analysis has shown why that is the case. Continuation of exercise 51. Derive a formula for tan, okay, this time A minus B. Do you notice something in the previous exercise besides this condition? I mean, about our approach to the solution. The thing is that when we are trying to do something for the first time, we will make mistakes and we will take silly steps like this. Maybe we are focusing on the wrong thing. It always happens. The important thing is that you should be able to overcome all the things and make your final conclusion correctly. That's what matters. And once you have your full solution, then you can trim it. Okay, you can remove these unnecessary parts and have that compact solution. Usually what happens when we look at a written solution, it's in the compact and nice form where all those trimmings have already been done. So we wonder, okay, how was this step thought of in the first place? No, we don't know. Only through such workings and such mistakes we get to know what to do. Okay, and then we write a short solution. Now here of course we are not going to go through all those things again. We are simply going to use this formula and derive this. So keep in mind here also that cos A cos B not equal to 0, that condition is there in the background. So without even thinking about that, we just simply write the solution like this. From the previous exercise, we have tan A minus B equal to tan A plus minus B. We can regard minus b as a single real number. So now you just use this formula, tan A plus tan minus b divided by 1 minus tan A tan minus b. If you are really minutely going through this condition and all these things, you can ask me, okay, you are saying, that means I am saying that cos A cos B is not equal to 0, but we don't have b here, we have minus b. So if cos A cos B is not equal to 0, then that is not exactly the condition that I need here. I need cos A cos minus B is not equal to 0, but that is just equivalent to this. Why? Because cos minus B is equal to cos B. This is something we already know. So cos A cos B not being 0 is the same as cos A cos minus B also not being 0. And now another similar thing. So for if you have tan here in place of cos, then we know that tan minus A is, or rather because we have minus b, so let me write b here, is minus tan b. This is something we already know. So let's just use that here. Tan A, so it will be minus tan b, and in the denominator this minus and that minus that's going to come from this one, they will give you plus tan A tan B. So this is the formula for tan A minus B. Next, the next one is a very interesting one. The next one involves a figure which I have to draw. Apply the law of cosines. to the triangle in the accompanying figure, or in the following figure. Let's just write that. In the following figure, to derive the formula for cos A minus B, and the figure is this. In the figure we have a circle, a unit circle, which of course I have to just simply draw like this as best as I can, and it's a unit circle whose center coincides with the origin of our coordinate system. This is the x-axis, this is the y-axis, usual stuff, x, y, and because it's a circle having radius 1, so this much is 1, this much is also 1, and this is our origin, of course. Now we have two angles here, A and B, and in the text or in the exercise, the angles have been drawn like this. It does not matter how exactly you draw this, roughly it's like this. This is B, this much is B, and this is A. Okay, now we have to apply the law of cosines. We already have seen the law of cosines in this section to this triangle, and from that application we have to derive a formula. A formula means we already know what the formula is. We have to derive that formula. How? Let's see. Solution. So note, is there something else that I am forgetting in this figure? No, that's just it. So this is what we are given. Now in this triangle, let's give the other vertices some names, no? So that we can refer to them easily. Say, let us call it C, and let us call this one D. So we have to accordingly write the things. Let's write like this. Let the terminal rays of the angles, terminal rays means this is B, so this is the initial ray of B and this is the terminal ray. The terminal ray of this angle B intersects the circle at the point C. So we are going to name them at once. Let the terminal rays of the angles B and A intersect the unit circle at C and D respectively. Actually, you should again draw the figure, because this is just the exercise. So in the exercise itself you do not do this. However, I am just saving space and time respectively. Fine. Then the coordinates of C are, note that we can directly write the coordinates of C. Why? Because we can use the definitions of sine theta and cos theta, sine B and cos B. Since this is your unit circle, this angle is B, whose terminal ray is this, that is intersecting the unit circle at this point. So by definition, the x coordinate of C will be cos B and the y coordinate of C will be sine B. So the coordinates are this. And just like that, because this angle is A and this is the terminal ray of that angle which intersects the circle at D, so the coordinates of D are cos A, sine A. Coordinates of C are cos B, sine B, and those of D are cos A, sine A. Now we are ready to apply the law of cosines on this triangle. So that means we have to recall the law. So we will recall it as we are applying it. So by the law, let me not write all these things. So by the law of cosines applied on the triangle OCD, we get this. So the law of cosines says that if you okay, by the way, what is this angle COD? That is A minus B, that means this much, this minus this. The law of cosine says this: CD square, that is the square of the side opposite to that angle, is equal to the square of the other two sides, I mean their sum, OD square plus OC square minus 2 times OD times OC times angle OCD, I mean COD. That is the law of cosines. Now we know CD square. That's because we have the coordinates of the ends C and D. So we can use the distance formula. So doing that, you will get cos A minus cos B whole square plus sine A minus sine B whole square. So this is CD square. Now note that OC and OD are radii, two radii of this same circle, which is the unit circle. So both of them are equal to 1. So 1 square plus 1 square minus 2 times 1 times 1, and this angle COD is, oh sorry, what have I written? Cos angle COD. Law of cosines, and I don't have cos here. Sorry about that. Cos A minus B. So now I will continue from here. So we now continue. So let's just expand these things. Cos square A plus cos square B minus 2 cos A cos B plus sin square A plus sin square B minus 2 sin A sin B is equal to 1 plus 1 is 2, 2 minus 2 cos A minus B. Okay. Now cos square A minus sin square A is 1, and we will get another one, cos square B plus sin square B. So these two ones give me 2 on the left hand side. What else do we have? Minus 2 cos A cos B minus 2 sin A sin B. So let's consider them together. Cos A cos B plus sin A sin B. This is equal to 2 minus 2 cos A minus B. And now you can clearly see that after the required cancellations, we have this, and we just switch sides. Cos A minus B is equal to cos A cos B plus sin A sin B. So this is our familiar cos A minus B formula, which we have now managed to derive from the law of cosines applied to this particular figure, this triangle. And the next exercise asks us to do a similar thing for cos A plus B, which however we won't do today. We will do it in the next calculus update, and further things will also come along with that. So I am ending things here itself. If you want to say something, you can use the comment section below, or you can mail me. My address will be there in the description. And tomorrow we are going to again solve algebra problems, group theory problems, specifically from your Gregory-Lee's algebra. And day after tomorrow, of course, we will resume our analysis. So that's just it. So I wrap things up for tonight. So see you tomorrow with Lee's algebra problems. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.